Hello, this is Dr. Priya Hassan, and this is the second lecture we have in this course on cosmology. So today I'll be talking to you about dark energy. Um, the last lecture you heard from Professor Hassan, where he told you about the expansion of the universe, which was discovered by Hubble using his observations. Now we have a new breakthrough which actually came in this in 1998 when two independent projects, the Supernova Cosmology Project and the High-Z Supernova Search Team, found out that this expansion was actually with an acceleration. Okay, and this actually came quite as a shock to everyone because people expected that maybe the expansion would slow down or continue at this constant pace, but for it to be accelerating was something was a total surprise. So let's now talk about how did they actually come across this discovery. Yeah, and so obviously, since it's a very important discovery, they received the Nobel Prize in 2011 for this. So you had Saul Perlmutter, you had Brian Schmidt, and you had Adam Rice, who were the recipients of the Nobel Prize in Physics in 2011 for this major discovery of the accelerating expansion of the universe. Now, what did they basically do? They basically used observations of supernovae. A supernova has already been defined to you. It's a powerful and luminous stellar explosion, and it's a transient astronomical event which occurs in the last stages of a massive star, or it could occur when a white dwarf is triggered into runaway nuclear fusion. Okay, and the type that they actually observed is the type 1a, which is associated to the white dwarfs. Now, what we need to remember about this is that supernovae are very bright explosions, right? And they are so bright that it's very easy to see supernovae in external galaxies, in other galaxies other than our own, because they are so bright. The other important thing about supernovae is that, like I've mentioned here, the supernova brightness is 5 billion times brighter than the sun. Here you have an example of a supernova remnant, which is a remnant from a type 1a kind of supernova. The other important thing about supernovae is that supernovae actually work as standard candles. Now, what are standard candles? So in astronomy, there are certain sources for which we can actually, through theory, predict the brightness of a source. And if you can predict the brightness of the source, then they can be used as standard candles. For example, if you have a 100-watt bulb and you put the 100-watt bulb at different distances, it's very easy for you, like you look in this figure, to actually compute the distances to that object. So here you have a candle which is close to you, and as it moves away from you, it actually becomes fainter. But since you know the brightness of this candle, when you look at the candle, you see the apparent brightness and you can infer the distance. So exactly like that for these galaxies over here, if you have a supernova over here, which is at some distance, you know its brightness. There's another galaxy where it's over here and another one it's over here. So using this, you measure the apparent brightness, but you know the absolute brightness. Like I showed you over here, the absolute brightness is minus 19.3. So what you can actually do is use this to actually get the distance to the supernova, right? And that's exactly what is done in standard candles. And so what they actually did was they actually looked at the supernova type 1a supernova in a whole range of galaxies over a whole range of redshifts. The idea was, in principle, you could say it would be in a way redoing what Hubble did, in the sense you then look at the spectra and you get their velocities using the formula we already did earlier, delta lambda by lambda is equal to v by c. So you look for the shift in the wavelength, and you can use that to actually get the velocities of these objects, right? And then you do what Hubble did, that is you plot velocity versus distance. And here is the plot of what Hubble had done. That is, on the y-axis he has velocity of the object, and on the x-axis he has distance. And like you see, what he got was almost a straight line fit, which he wrote as v is equal to h into d, where h is Hubble's constant. So you can see this is a direct straight line fit, which is a plot of this thing, right? Hubble's plot looked a little different. This is a much more revised version of it. So this is exactly what they actually tried to do. But when they actually did this, they discovered that this velocity is actually increasing. It is not a constant which you're going to get. And therefore, what they discovered was this, is that objects in the universe are moving away from another at an accelerated pace. Okay, and the acceleration expansion, if you look at the redshifts that you're looking at, you can actually see that the acceleration expansion, the accelerated expansion began 4 billion years ago. So here you can see in this plot, here you can see if you actually plot for accelerating universe and decelerating universe with the observed magnitudes of these objects at different redshifts. You can see the redshifts put over here, which actually go in terms of the time, right? How far back in time you are getting. And they actually found that their points, the two teams we spoke about, the High-Z supernova search are the red points, and the supernova cosmology project were this. So you actually had the two teams doing a similar job in slightly different ways. And you can see that how well their points confirm. And they actually confirm to a clear fit of an accelerating universe. So you actually get it as that. Now the question was, if these galaxies are being accelerated, right? We know gravity will actually cause these galaxies to come together, right? But in this case, we actually have the galaxies going away from another. So this is some kind of a negative gravity kind of a thing, which was given the name dark energy, right? Now, within the framework of general relativity, if you actually apply general relativity, gravity can be also compared to the curvature of space-time, right? Because you say that the curvature is actually what causes the gravitational force, right? And therefore, we will not go into those details, but in relativity, this can be compared to what is called a cosmological constant, lambda, which is also the equivalent to the presence of a positive vacuum energy, which was called the dark energy, right? So this dark energy can be also related to parameters in relativity, and that's what people do in general relativity, right? And this was obviously energy and not matter. People have often confused dark matter and dark energy. Dark matter, like we spoke about earlier, was the stuff which we have around galaxies, which causes stars to move around faster in the outer regions of galaxies as per the rotation curves that we've seen. And that's what we call dark matter, because dark matter shows its presence in terms of gravity, but does not radiate. In the case of this case, this is not matter, right? Because if it was matter, it would have actually shown an attractive force. In this case, we have an opposite force, which we can call negative pressure, with which these galaxies are actually moving away from another, right? And the other thing is that this is not exactly dark matter. It is just that it's transparent. Light travels through it. So it's not exactly what we call this thing, but it is some kind of energy which has a property of negative pressure, which is causing acceleration of these galaxies. Now, we will come to this later on, but using these things, we actually had some probes. I will come into the details in just a bit about how we actually got estimates of how much of dark matter and how much of dark energy we have in our galaxy. We'll talk about that soon. So if you actually use this data to trace back the evolution of the universe, you would see that from the point of the Big Bang, you initially had a slower expansion. And then from a period of about 7.5 billion years, you have an accelerated expansion of the universe, which is shown in this figure over here. So you can see that you started off with this, a slower expansion, and then an accelerated expansion. And this accelerated expansion is caused by a mysterious dark force that is actually pushing galaxies apart. Now, let us try to understand how do we actually make estimates of dark matter and dark energy. Now, this is based on what is called the on the basis of this is the cosmological principle. The cosmological principle basically tells you that when you look at large scales, at very large scales of megaparsecs, etc., you actually notice that the universe is homogeneous and isotropic. So by homogeneous, you mean that all properties of the universe are the same everywhere. So if you were to apply some laws of physics and a certain properties in a certain part of the universe, it will also apply to other parts of the universe, right? Isotropy obviously means that it is the same in whichever direction you look at it, right? So basically this implies that we observe no observable irregularities in the large scale structure over the course of evolution of the matter field that was laid down by the Big Bang. This is the cosmological principle. Now you were already told about this thing which is called the cosmic microwave background radiation. Now, obviously, like when you have the Big Bang, right? If you had a big fire or a big this thing of energy, you do expect that even after 13.7 billion years, there has to be some amount of relic radiation or some radiation which is left over from the Big Bang. Okay. Now, the Big Bang people had already predicted that we actually need to look for this radiation, which is the relic radiation of the Big Bang. And it was actually a purely accidental thing through which Penzias and Wilson, they were actually working for Bell Labs and they were looking for actually disturbances in the signals. And that's when they discovered that using this horn antenna of theirs, that whichever direction they pointed out towards the sky, there was a certain amount of a hum coming from everywhere. And this is what was called the cosmic microwave background radiation. Now, whatever they did, there was no way they could actually avoid this thing. And that's when they realized, when they spoke to scientists, they realized that this was actually nothing but the cosmic microwave background radiation that people were looking for since ages. And for this work, they actually got the Nobel Prize in 1978. Now, basically what the CMB says is that whichever direction you look on, you have this radiation coming. What was actually next investigated by NASA using a satellite called the COBE satellite, which is a Cosmic Background Explorer satellite, was they basically tried to explore whether this radiation is uniform. Is it the same in all directions, right? So COBE actually mapped it. That is, yeah, and like I said, since this radiation is very feeble, it was necessary to look for it in space and not from the Earth so that you don't have any other disturbances and so that you can catch this feeble radiation. So what COBE did is actually it made a map of the CMB, which you can see up over here. So you had hot spots and cold spots. And basically by hot and cold, you mean a slight variation in the radiation in different directions, which you had the red and the blue points, right? Now, this was a very difficult job which was done, and it was done by Smoot and Mather, for which they also received the Nobel Prize in 2006 for the work on this project, on the COBE project. It was obviously realized that their further improvement was required in the COBE results, and therefore NASA launched a second CMB project mission, which was called the WMAP in 2001. So 2001 was called the Wilkinson microwave anisotropy probe because it was already known that we do have an anisotropy, and what WMAP tried to do was to actually measure this isotropy very well. So there's 9 years of observations, and they finally released a map of this anisotropy. Now note that the anisotropies which WMAP got were actually 10 parts per million, that is 10 power minus 5. So the coloring which you see in this map, which is very obvious to the eyes, is actually artificially imposed because the differences between the brightnesses are of the order of 10 power minus 5, right? So we have actually, the map actually accentuates that so that you can see the difference. But in principle, please note that this difference is 10 parts per million, right? So this does not violate the cosmological principle. It's not saying that now the universe is not homogeneous or not isotropic. It is still very much homogeneous and isotropic till the accuracy of 10 power minus 5, right? The 5th decimal place. That's the kind of ratio you'd have between the brightnesses of these different parts of the map. Following WMAP, ESA, which is the European Space Agency, they also had another project of their own, which was called Planck. And Planck basically operated from 2009 and to 2013. And what it basically did is it improved on the WMAP results with a much higher resolution and much higher sensitivity, right? So what you have on the right over here is an image of Planck. So what you can see is that now the picture that we have of the universe, how do we actually think that the universe formed, is that the universe was built bottom up, right? So this is actually a period very in the early parts of the universe, which you're actually seeing the CMB. It belongs to a very early age of the universe. And that's when you can see that you have these very small anisotropies in the universe. And what they basically do is that they work as gravitational seeds, right? And so therefore what happens is overdense regions, they attract more matter, while underdense regions attract less. And thus the overdense regions become denser and denser, and they increase the anisotropy. And that's how you actually produce large scale structures in the universe. So this is our understanding of how the universe actually managed to create so much of structure, which we actually see that galaxies belong to groups, to clusters. There are filamentary structures, there's a web, and which we can actually see, which can be very well explained using this kind of an understanding of the buildup of large-scale structure from small anisotropies which existed in the early universe. So here I have another picture which actually shows the comparison between Kobe, WMAP, and Planck, and you can actually see the kind of difference you have. So Kobe is actually giving you a resolution of 7 degrees, while Planck jumps to 0.07 degrees. That's the kind of accuracy that you're getting. We also have to note that the CMB is coming from a part when the universe was only 380,000 years old. So it's a very early event in the formation of the universe, when we actually see these anisotropies, right? Now, how do we relate this to our understanding of dark energy, etc.? So what actually we do is that depending upon like I said, the amount of gravitational force, etc., in the universe, in also dark energy, will actually cause a curvature of the universe. So the universe could be closed, flat, or open. So if you look over here, if you have a closed universe, you would actually see you would see that the light from opposite sides of a hot spot, they actually bend towards each other. And therefore the hotspot appears to us larger than it actually is. You could also have a flat universe where there's no difference. And if the universe was open, then the light rays from opposite sides of the hotspot bend away from each other. And therefore, by very detailed study of the maps that we get from WMAP as well as Planck, we can actually get an estimate of the amount of dark energy. So what you can see over here is that these are the most precise results we have. That is, before Planck, this was our understanding of the universe, that 4.5% of the universe was ordinary matter, and 22.7% was dark matter, and 72.8% is dark energy. Now, Planck has further improved these numbers with smaller error bars, and therefore now after Planck, what we know is that 4.9% of the universe is what we know, the ordinary matter that we live in, and dark energy comprises 68.3%, while dark matter is 26.8%. And therefore, we can actually get an estimate of the composition of the universe using these kind of studies. I also wanted to introduce you to that for structure formation. Obviously, a very large amount of role is played by computer simulations, right? Because when we can't observe, what we do is we use our data, our values that we have, to actually simulate the universe and actually try to see structure formation. Another way of also doing this kind of work is also by doing gravitational microlensing. Now we know that gravity, since it curves space and time, it actually behaves like a lens, right? So we can actually look at objects and look at microlensing from the objects to estimate the amount of mass, right? And this is also done to estimate these parameters. So what have we seen is that accelerating universe was discovered using supernova experiments, but it is also supported by a whole bunch of other experiments and other observations. So there was, in 2000, there were some CMBR balloon experiments also which supported this. There is also the baryon acoustic oscillations, which are also used to study the large scale structure of matter. There are microlensing experiments. There was the BICEP experiment, which has its own issues. And basically, by looking at the growth of large-scale structure and the observed values of cosmological parameters, the thing is definite that yes, we do have an accelerating universe, but the parameters of it are what we are trying to further investigate. So these are definitely very exciting times ahead, where we do expect to see a lot of interesting things. And I'll wind up over here with a cosmological simulation, where you can actually see um, the kind of this is a simulation of structure formation in the universe. What you can see on the upper right is is the age of the universe from the time it was born, and here you can see the corresponding redshift, and we can actually see how basically structures form in the universe, right? So here is the thing at this large redshift at an early age of the universe. And you can see that initially there are these very small gravitational seeds, which are the inhomogeneities, which we saw in the beginning. And then as time progresses, these inhomogeneities become more accentuated. Well, I think I increased the speed a bit too much, and we'll reduce it. So here we can see that I increase the inhomogeneities, and gradually you can see there's proper structure formation over here. So you can see that these nodes, etc., these are where clusters of galaxies are forming. Galaxies are forming, and you can see the scale of the universe. And if you Google and say, you'll actually see that there are a whole lot of cosmological simulations available on the internet. So people are using a lot of computing power and a lot of theory into understanding and trying to actually build up cosmological simulations and see how exactly the universe was formed, right? So now we are getting to more present times. You can see as the redshift reduces, redshift 0 is our present time. And these are earlier epochs of the universe where you can actually see structure is being formed and you can actually form the universe. So people actually simulate and actually form the universe, form structures in the universe, and use this to actually make estimates of dark matter, dark energy, and various other parameters of the universe, which we are now trying to explore, right? So I'll end with this thing, and do have a look at the other computer simulations that you'd find on the net on structure formation in the universe, right? Yeah, that's our present time, and that's we stop. So thank you so much.